What if I told you the countdown has already started? Not to impact, not to disaster, but to something potentially more disruptive. The moment when millions of people look up simultaneously and see something that shouldn't be there. 3I-ATLAS, officially classified as a comet, will make its closest approach on December 19th. And if independent observers are right about its brightness trajectory, if those unexplained flares they've been documenting turn out to be real, it could become visible to the naked eye. A point of light from another stellar system hanging in our sky, refusing to behave exactly as models predict. The question isn't whether to watch. The question is whether you're ready for what happens after, because I'm going to walk you through the readiness protocol, the preparations happening quietly in government facilities, and the scenarios that keep people with security clearances checking the data one more time before they sleep. If you're as captivated by these cosmic puzzles as I am, go ahead and like this video and subscribe so you catch every development as December 19th approaches. Leave a comment telling me where you're watching from, what your local time is right now, and whether you think the official story about 3I-ATLAS is everything we need to know. Part 1, December 19th, the night the sky stops being ours. The calendar says December 19th, 2025. Your phone says it's just another Friday, but what if I told you that date might mark the moment when humanity's relationship with the cosmos changes forever? Not because something will hit us, not because we're in danger of impact, but because for the first time in recorded history, an object from another star system will pass close enough that some observers believe we might see it with our naked eyes, and that simple act of seeing could trigger a cascade of questions we're not prepared to answer. The object is designated 3I-ATLAS, and according to widely circulated data, it will reach its closest approach to Earth on December 19th, sitting roughly 1.8 astronomical units away. That translates to about 270 million kilometres, which sounds impossibly distant until you realise that astronomical visibility isn't about proximity. It's about brightness, and brightness, when you're dealing with an interstellar comet that's been bathed in cosmic radiation for potentially millions of years, can be unpredictable in ways that make astronomers very, very nervous. Let me be clear about something up front. The mainstream scientific consensus places 3I-ATLAS at a magnitude of around 11 to 12 at closest approach. That's firmly in telescope territory, nowhere near the threshold of magnitude 6 or brighter that would make it visible to the unaided human eye under dark skies. But here's where things get interesting, and by interesting I mean deeply unsettling. Some independent observers and online astronomy communities have been tracking unusual behaviour in the object's light curve. They're reporting sporadic brightening events, what some call flares or pulses, that suggest the comet's activity might be far more dynamic than official channels are letting on. The hype around potential naked eye visibility didn't emerge from nowhere. It stems from a fundamental truth about comets, especially interstellar ones. They're volatile. Their composition determines how they react to solar heating, and 3I-ATLAS has a composition that reads like it came from a completely different cosmic cookbook. When the James Webb Space Telescope turned its infrared gaze toward this visitor, it found something unusual. The coma, that fuzzy envelope of gas and dust surrounding the nucleus, is dominated by carbon dioxide. Not water, not the typical mix we see in solar system comets. Carbon dioxide with traces of water, carbon monoxide, dust and various ices, creating a chemical signature that screams foreign origin. Why does a carbon dioxide-dominated coma matter? Because it tells us this object formed in conditions radically different from the icy bodies native to our solar system. It likely coalesced in a colder, more volatile-rich region around another star, perhaps in the outer reaches, of a planetary system where temperatures hover just above absolute zero. And when an object like that enters our solar neighbourhood and starts getting cooked by our sun, all bets are off regarding how it will behave. Carbon dioxide sublimates, turning directly from ice to gas at temperatures where water ice remains stable. This means 3I-ATLAS could experience outgassing events, sudden releases of trapped volatiles that would make it flare dramatically in brightness without warning. Imagine standing in your backyard on December 19th, looking up at a sky you've known your entire life, and seeing a new point of light that wasn't there yesterday. A point of light that doesn't belong to any constellation, doesn't follow the predictable paths of planets or satellites. A point of light from somewhere else, somewhere impossibly far away. The psychological impact of that moment would ripple through society in ways we can barely anticipate, because suddenly, Viscerally, humanity would confront a truth we've always known intellectually, but never felt emotionally. We're not alone in the universe, not in the sense of intelligent life necessarily, but in the undeniable fact that matter from other star systems can arrive in our cosmic backyard, carrying with it the chemistry and history of alien suns. The scientific community has tried to manage expectations, emphasizing that 3I-ATLAS is behaving like a comet, following predictable physics, showing no signs of anything beyond natural phenomena. But science deals in probabilities and confidence intervals, not certainties. And when you're studying the second or third confirmed interstellar object ever observed by humanity, the sample size is so small that every assumption carries enormous uncertainty. We've never tracked an object like this through a complete solar encounter. We've never had instruments sensitive enough to detect the subtle variations in brightness, composition, and trajectory that might hint at something more than simple ice and rock. Here's the central question that will haunt the next few weeks. If 3I-ATLAS does brighten unexpectedly, if those independent observers reporting flares turn out to be documenting something real, what would that mean? A structural collapse as volatile rich pockets explode? A cryovolcanic eruption from deep within the nucleus? Or, in the most speculative corners of discussion forums and late-night conversations among amateur astronomers, could it represent a change in the object's orientation or activity state? Something that suggests a level of structure or purpose we're not supposed to find in a lump of ancient ice. The stakes extend far beyond astronomy. Even without impact risk, a surprisingly visible interstellar object would generate enormous public attention, intense speculation, and profound pressure on institutions to explain what they're seeing. It would force conversations about cosmic visitors, about the nature of interstellar space, about what else might be out there travelling between the stars. It would challenge the comfortable narrative that Earth exists in a relatively quiet, empty region of space, where such encounters are vanishingly rare. And it would do all of this at a time when humanity is already grappling with rapid technological change, geopolitical instability, and a growing sense that the old certainties no longer hold. So yes, December 19th is just another date on the calendar. But it might also be the night when millions of people look up and realise the sky isn't ours anymore. It never was. We just forgot that every photon hitting our eyes has travelled through an incomprehensible vastness, carrying information about places and processes we can barely imagine, and now one of those places has sent us a visitor, whether we're ready or not. Part 2. The Data War. Why agencies can't agree on the light curve. Numbers should be objective. Data should tell a clear story. But when you're trying to track a city-sized chunk of ice and rock from another star system, as it barrels through the inner solar system, clarity becomes the first casualty. The scientific community finds itself in an uncomfortable position, caught between competing datasets that paint wildly different pictures of 3I-ATLAS's behaviour. And this isn't just academic squabbling. The discrepancies in brightness measurements and light curve interpretations have real implications for how we understand this object and what we should expect in the coming weeks. Photometry seems straightforward enough on paper. You measure the apparent magnitude of an object, how bright it appears from Earth, and track how that brightness changes over time. Plot those measurements, and you get a light curve, a graph that reveals patterns in the object's activity. For comets, light curves can show periodic variations due to rotation, sudden spikes from outgassing events, or gradual changes as the comet approaches or recedes from the Sun. Simple in principle, maddeningly complex in practice, especially for an object exhibiting behaviour that doesn't quite match the playbook written from centuries of observing solar system comets. Amateur astronomers with backyard telescopes and CCD cameras have been posting data to online forums showing something curious. They're detecting brightness variations that seem to come in bursts, irregular pulses of light that appear and fade over hours or days. Some claim to see a pattern, a rough periodicity that might indicate the nucleus is rotating with active jets pointing in different directions, creating a lighthouse effect as they sweep past Earth's line of sight. The problem is that these observations are happening at the edge of detectability, where atmospheric turbulence, instrument sensitivity, and background sky brightness all introduce noise that can masquerade as real signals. Now contrast that with the data coming from institutional telescopes. Large ground-based observatories and space-based platforms like the James Webb Space Telescope report more conservative measurements. Their light curves show a generally stable object with brightness variations that can be explained by the standard model of cometary activity. Outgassing driven by solar heating, producing a coma that scatters sunlight in predictable ways. Some variation, yes, but nothing that screams anomaly, nothing that requires exotic explanations. The discrepancy isn't necessarily that one group is wrong and the other right, it's that they're measuring different things at different times with different instruments that have different strengths and weaknesses. Here's where things get weird, and I want to be very clear about the line between observation and speculation. Some independent observers have started talking about a pulse cycle. They claim 3I-ATLAS brightens and dims on a roughly 11 to 16 hour schedule. Too regular to be random, too irregular to be simple rotation. Online astronomy communities have filled spreadsheets with photometric data trying to find the pattern, arguing over whether they're seeing evidence of multiple active regions on a rotating nucleus, tidal stress causing periodic cracking and gas release, or something that doesn't fit comfortably into the natural phenomena box. None of this has been verified by peer-reviewed science. None of it has been confirmed by the institutions whose job it is to track these objects, which is exactly what makes it so unsettling. The data war matters because it shapes narrative. If you trust the institutional measurements, 3I-ATLAS is a comet behaving like a comet, interesting primarily because of its interstellar origin, but ultimately unremarkable in its behaviour. If you give weight to the amateur observations, suddenly you're dealing with an object exhibiting patterns that might indicate something more complex. Structured activity, rhythmic variation that could hint at internal processes we don't understand or haven't seen before. And in the age of instant communication and social media amplification, both narratives spread simultaneously, creating confusion and fueling speculation. Why would agencies downplay unusual brightness patterns? The charitable explanation is that they're being scientifically conservative, refusing to endorse claims until they meet rigorous standards of evidence. The less charitable interpretation is that they're managing public perception, trying to avoid headlines that would spark panic or draw attention away from other priorities. Consider the institutional incentive structure. NASA and other space agencies are juggling multiple missions, competing for limited budgets, operating in a political environment where sensationalism can derail careful planning. If 3I-ATLAS turns out to be just another comet, any premature hype about anomalous behaviour would damage credibility. Better to understate than overstate. Better to wait for certainty than risk being wrong in public. But what if some observers are documenting something real? What if those brightness spikes represent genuine outgassing events? Jets of sublimating carbon dioxide erupting from subsurface pockets as they're heated by the sun. What if the periodicity reflects actual rotation of an irregularly shaped nucleus with active regions that face Earth on a predictable schedule? Those would be natural explanations, fascinating scientifically but not paradigm-shifting. They would tell us about the internal structure and composition of interstellar objects, about how volatile ices behave after spending eons in the deep freeze between stars, about how objects formed in other planetary systems differ from our familiar comets. The alternative, the explanation that lives in the uncomfortable space between speculation and paranoia, is that brightness variations might indicate something else entirely. A change in surface properties as ancient irradiated crusts crack and expose fresh material. A venting event that's controlled rather than random, releasing volatiles in patterns that suggest internal structure or deliberate timing. Or, in the most extreme interpretations floating through certain corners of the internet, a change in the object's energy state, something that would require us to reconsider what we're actually looking at when we point our telescopes at this visitor from the stars. I'm not endorsing that interpretation. I'm not claiming 3I-ATLAS is anything other than what mainstream science says it is. But I am pointing out that we're in uncharted territory with a sample size of 1, trying to understand an object whose behaviour may not conform to patterns established by studying residents of our own solar system. And in that uncertainty, in that gap between what we know and what we're observing, speculation finds fertile ground. The data war isn't going to resolve itself before December 19th. We're going to hit closest approach with competing narratives still in play, with both amateur and professional observers watching the same sky and seeing different things. And that ambiguity, more than any confirmed anomaly, might be what really unsettles people when they look up and wonder what's really out there. Part 3. Trajectory refinements and the 0.0. 0.003% claim. No one wants to discuss. Objects in space follow rules. Gravity pulls them into predictable orbits, curves their paths around massive bodies, creates elegant mathematical relationships between position, velocity, and time. We've been doing this calculation for centuries, predicting planetary positions with enough precision to land rovers on Mars and thread spacecraft through the gaps in Saturn's rings. So when an interstellar object enters our solar system, we should be able to plot its course with similar confidence, tracking where it came from and where it's going with the cold certainty of Newtonian mechanics. Except 3I-ATLAS isn't quite following the script, and the tiny deviations from expected behaviour have some researchers nervously checking their calculations and others whispering about possibilities nobody wants to say out loud. Let me explain what we mean by hyperbolic trajectory. When an object is gravitationally bound to the Sun, it follows an elliptical orbit, returning periodically like comets native to our solar system. But 3I-ATLAS is moving on a hyperbola, a path that brings it in once and sends it back out to interstellar space, never to return. The mathematics are clear. This visitor has excess velocity beyond what the Sun's gravity can capture. It came from somewhere else, passed through our neighbourhood, and will leave carrying stories of our star system back into the void between stars. That part isn't controversial. The controversy lies in the details of how it's moving. Comets don't travel on purely gravitational trajectories. As they heat up near the Sun, volatile ices sublimate, turning directly from solid to gas and venting into space. Those jets of gas create thrust, tiny rocket engines that push the comet in directions determined by where the active regions are located and which way the nucleus is rotating. Astronomers call these non-gravitational accelerations, and they're expected, normal, part of how comets work. We account for them in trajectory calculations, adjusting our models to include the gentle push from outgassing. For 3I-ATLAS, those calculations should be straightforward. We know it's outgassing. We've detected the carbon dioxide coma. We can estimate the thrust based on the observed activity. Should be simple. Here's where the numbers get interesting. The nucleus of 3I-ATLAS is estimated to be somewhere between 440 metres and 5.6 kilometres in diameter, a range that reflects the uncertainty in measuring an object so far away, exhibiting non-standard reflectivity. Using those size estimates and the observed outgassing activity, scientists can model how much thrust the comet should be experiencing. They can predict how much its trajectory should deviate from a purely gravitational path, and when they run those calculations and compare them to the actual observed trajectory, most researchers find that everything matches within acceptable error bars. The non-gravitational acceleration is consistent with outgassing from a comet of that size and composition. Case closed. Except a small number of independent analysts, some with legitimate credentials in orbital dynamics, argue that the match isn't quite as clean as official statements suggest. They point to subtle residuals in the trajectory, tiny unexplained deviations that persist even after accounting for expected outgassing. They suggest that the observed acceleration is slightly higher than models, predict by a small but measurable amount that opens the door to alternative explanations. And here's where we get to the number nobody wants to talk about, 0.0003%. That's the claimed probability, according to some of these analysts, that 3I-ATLAS's trajectory requires something beyond standard cometary outgassing to fully explain. Something else providing thrust. Something that would make this object behave in ways we don't expect from a lump of ancient ice. Let me be absolutely clear about what that number means and doesn't mean. It's not a probability that 3I-ATLAS is artificial. It's not a calculation that proves alien engineering. It's a statistical estimate of how well current models match observed data, and the claim is that there's a tiny, nearly infinitesimal gap that could, in principle, allow for alternative explanations. It's the kind of number that in any other context would be dismissed as measurement uncertainty, instrumental noise, modelling assumptions that don't perfectly capture reality. But this isn't any other context. This is an interstellar object, only the second one we've studied in detail, and the first one, Oumuamua, had similar problems with unexplained accelerations that sparked years of debate and speculation. The comparison to Oumuamua is instructive and troubling. That elongated visitor exhibited non-gravitational acceleration that couldn't be easily explained by outgassing, because it showed no detectable coma, no visible gas or dust that would create thrust. Researchers proposed various natural explanations: outgassing of pure hydrogen that would be invisible, or light pressure on an unusually reflective surface, or tidal forces creating structural stress. All plausible, all requiring assumptions that push the boundaries of what we typically see in solar system objects. And while most scientists accepted these explanations, a small but vocal minority continued arguing that Oumuamua's behaviour was, to use their phrase, problematic in ways that standard comet models couldn't fully address. Now we have 3I-ATLAS showing similar issues, albeit at a much smaller magnitude. The unexplained component of its acceleration is tiny, barely detectable, well within the realm where measurement uncertainty and modelling assumptions could explain everything, but it's there. And for those inclined to see patterns, it's another data point suggesting that interstellar objects might behave differently than we expect based solely on studying residents of our own solar system. Maybe interstellar space does things to these objects during their millions of years' journey between stars. Maybe cosmic ray bombardment, temperature cycling between near absolute zero and the heat of stellar approaches. Maybe these processes create internal structures or surface properties that affect how they outgas and respond to solar heating. Or, in the speculative scenario that lives in the margins of serious discussion, maybe something about 3I-ATLAS's trajectory suggests intentional adjustments. Not dramatic course corrections, not obvious manoeuvring, just subtle deviations that could, if you squint at the data the right way, hint at a level of control inconsistent with random outgassing. A stabilization system keeping the object oriented in a particular way. An asymmetric vent design that creates thrust in predetermined directions. Hidden mass distribution that affects how the object responds to external forces. I'm not claiming any of this is true, I'm pointing out that the mathematical door is open. Just a crack. Just enough to let speculation seep through. Why does a 0.0003% chance matter? Because in a probabilistic universe, non-zero means possible. And for a global population primed by decades of science fiction and cosmic speculation, that tiny probability becomes a foothold for imagination. It becomes the thread that, when pulled, unravels comfortable assumptions about what we're observing. It transforms 3I-ATLAS from a scientifically interesting, but ultimately mundane comet into a cipher, an object that might be more than it appears, carrying secrets in its trajectory that we lack the context to interpret. The next few weeks will tell us more. As 3I-ATLAS continues its outbound journey, as more observations accumulate and trajectory calculations refine, that 0.0003% could shrink to zero, or it could grow. It could become clear that standard models explain everything perfectly, or it could become obvious that something about this object doesn't quite fit the patterns we expect. Either way, we're learning that interstellar space is not empty, that objects from other star systems visit ours more often than we once believed, and that every visitor brings questions we're not fully prepared to answer. And if someone, somewhere, is paying closer attention than they're letting on, watching 3I-ATLAS with more than just scientific curiosity, well, we'll get to that in the next part. Part 4. Why intelligence agencies quietly activated Passive Observation Protocol Z. Science is supposed to be transparent. Public observatories publish their data. Research papers undergo peer review. Discoveries get announced in journals and press conferences, shared with the world as contributions to collective human knowledge. But there's another layer of observation that doesn't appear in astronomical bulletins or NASA press releases. A layer where instruments designed for different purposes can be quietly retasked when something unusual appears in the sky. And according to fragmentary reports and carefully worded statements from officials who may know more than they're saying, 3I-ATLAS has attracted attention from organisations that don't typically concern themselves with comets. Let me introduce a concept I'm calling Passive Observation Protocol Z, a working name for what appears to be a coordinated but low visibility monitoring effort focused on this interstellar visitor. The passive part means no active interrogation, no radar pinging or laser ranging that would advertise our attention, just listening, watching, collecting every photon, every radio emission, every particle of data that crosses the gulf between 3I-ATLAS and Earth's detection networks. The protocol part suggests a predetermined plan, a playbook for how to respond when something enters our solar system that doesn't quite match expectations. And the Z designation? That's pure speculation on my part, but historically, the letter Z gets attached to plans and protocols reserved for contingencies nobody expects to use. The just-in-case scenarios that sound paranoid until they're not. We know from public records that 3I-ATLAS has received unprecedented attention from space agencies worldwide. The International Asteroid Warning Network, usually focused on potentially hazardous near-Earth objects, has dedicated resources to tracking this visitor, despite its zero-impact probability. NASA's heliophysics spacecraft, designed to study the sun and solar wind, have been imaging 3I-ATLAS as it moves through the inner solar system. This marks the first time these instruments have captured an interstellar object, creating a data set that blends solar science with interstellar visitor studies in ways that weren't planned when those missions launched. The coverage is comprehensive, sustained, and suggests a level of coordination that goes beyond normal scientific interest. But here's where things drift from confirmed fact into informed speculation. Deep space monitoring networks exist that serve dual purposes. Radio telescopes can listen to pulsars and search for extraterrestrial intelligence, but they can also detect artificial transmissions or structured emissions from objects passing through the solar system. Very low-frequency arrays designed to study Earth's magnetosphere and upper atmosphere can pick up electromagnetic signatures from space, potentially including plasma interactions or electrical activity around comets. These instruments weren't built to study 3I-ATLAS specifically, but they can be retasked when something interesting appears, and the data they collect doesn't always make it into public archives. I want to be very clear about what I'm claiming and what I'm not. I'm not saying intelligence agencies have detected alien signals from 3I-ATLAS. I'm not claiming there's classified data proving this object is artificial. What I am saying is that when an interstellar visitor exhibits behaviour that generates scientific uncertainty and public speculation, it would be extraordinary if security and intelligence organisations didn't take notice. They have a mandate to monitor potential threats, to assess unknowns, to gather information about phenomena that could impact national or global security. An object from another star system, moving through our cosmic neighbourhood, possibly behaving in ways that push the boundaries of comet models, that absolutely falls within their area of interest. Online communities, particularly those focused on amateur astronomy and fringe science topics, have reported something curious. Posts describing unusual, very low-frequency noise detected by hobbyist monitoring stations, electromagnetic signatures that some claim correlate with the timing of 3I-ATLAS's reported brightness flares. These reports are anecdotal, unverified by professional instruments, and could easily be artifacts of local interference or instrumental glitches, but they're persistent, showing up across different monitoring stations in different locations, suggesting that if nothing else, people are paying attention and comparing notes in ways that might reveal patterns invisible to any single observer. Historical precedent gives some context for how this might play out. During the Cold War, when a particularly bright meteor exploded over the Soviet Union, US intelligence satellites designed to detect nuclear weapons tests captured the event, providing data that eventually helped scientists understand large asteroid impacts. More recently, classified instruments have detected meteors that weren't seen by public networks, their data released years later after military sensitivity expired. The relationship between security infrastructure and cosmic observation has always been closer than most people realise, with dual-use technologies providing both strategic intelligence and scientific insights. If that infrastructure is currently pointed at 3I-ATLAS, we might not know for years, if ever. Why keep observation quiet rather than public? Several reasons come to mind. First, avoiding premature conclusions that could spark panic or misunderstanding. If instruments detect anomalous signals or unexpected behaviour, better to verify thoroughly before making announcements that can't be taken back. Second, maintaining observational advantage. If there's any possibility, however remote, that 3I-ATLAS might be more than a comet, you'd want to gather as much data as possible before tipping your hand. Third, managing international dynamics. Space is increasingly contested territory, with nations competing for access and prestige. A discovery related to an interstellar object could have implications for how we think about space security, planetary defence, and the protocols for responding to unusual phenomena. There's another possibility worth considering. Maybe passive observation protocol Z isn't primarily about 3I-ATLAS itself, but about how we respond to it. A dress rehearsal for future encounters with interstellar visitors, testing our detection networks, our data sharing protocols, our ability to coordinate international responses to cosmic unknowns. In this interpretation, the object matters, less than the exercise of tracking it, evaluating it, and preparing for the possibility that future visitors might require more than just telescopes and scientific curiosity. We might need rapid assessment capabilities, communication protocols that span agencies and nations, and frameworks for deciding how to share information with the public when we don't fully understand what we're observing. As December 19th approaches, you can bet that somewhere, in facilities with restricted access and instruments that don't appear in public catalogues, people are watching 3I-ATLAS very carefully. They're collecting data that might never be published. They're running analyses that won't show up in peer-reviewed journals. And they're asking questions that sound paranoid in public, but are perfectly reasonable when your job is to prepare for contingencies that haven't happened yet but could. Whether that preparation is prudent caution or unnecessary paranoia depends on what the next few weeks reveal. But either way, the sky is being watched by more eyes than most people realise, and not all of those eyes belong to astronomers. Part 5. The first 72-hour window, why preparations start before the flyby. Time compresses as deadlines approach, the weeks and months of tracking. 3I-ATLAS, the slow accumulation of data points and trajectory refinements, the gradual building of scientific understanding, all of that collapses into a narrow window where decisions must be made and actions taken based on incomplete information. We're talking about the 72 hours before closest approach on December 19th, the period when uncertainty peaks, and the gap between what we know and what we need to know becomes critically important. This is when preparations shift from theoretical contingency planning to concrete readiness measures, when abstract discussions about interstellar visitors become operational questions about how to respond if something unexpected happens. Governments and institutions that take risks seriously, that plan for low probability but high impact events, they operate from playbooks designed for situations just like this. The playbook for an interstellar object with zero impact probability but uncertain behaviour includes several components. First, final data consolidation, bringing together observations from all available sources to create the most accurate possible picture of the object's position, trajectory, brightness, and composition. This involves coordination between observatories, space agencies, research institutions, each contributing their piece of the puzzle to a composite understanding that no single organisation could achieve alone. The data goes to modelling teams who run simulations, calculating not just what's most likely to happen, but also exploring the tails of the probability distribution, the unlikely but possible scenarios that require different responses. Second, communication strategy development. Someone has to decide what information gets released to the public, when, and through what channels. Do you emphasise the scientific consensus that 3I-ATLAS is a well-behaved comet? Do you acknowledge the uncertainties and conflicting data that have generated speculation? Do you address the fringe theories head-on or ignore them and hope they don't gain traction? These questions don't have obvious answers, and the choices made in those 72 hours will shape how the public perceives and responds to closest approach. Get it wrong, and you either feed panic through excessive alarm or breed mistrust through excessive reassurance that feels like dismissal of legitimate questions. Third, there are operational readiness measures that sound paranoid until you think through why they might be necessary. Communications infrastructure gets extra scrutiny during this period. Satellite networks that handle internet traffic, GPS signals, financial transactions, they all depend on precise timing and stable connections. If there were any possibility that 3I-ATLAS could generate electromagnetic effects, plasma interactions, or other phenomena that might interfere with space-based systems, this would be the time to ensure backup capabilities are ready. Not because we expect problems, but because the cost of being unprepared vastly exceeds the cost of having redundant systems on standby that end up not being needed. Emergency services briefings might sound excessive for an object with zero impact risk, but consider what happens if public perception shifts suddenly. If 3I-ATLAS brightens unexpectedly and becomes visible to the naked eye, if social media erupts with speculation and theories, if the narrative shifts from comet to unknown, you'd want first responders and local authorities prepared for potential social disruption. Not riots or apocalyptic chaos, but the kind of confusion and anxiety that constrain systems designed to handle everyday emergencies. A surge in 911 calls from people seeing something strange in the sky. Traffic accidents from distracted drivers looking up instead of at the road. Mental health crises triggered by individuals whose grasp on reality is already fragile, encountering something that confirms their worst fears or validates their most extreme beliefs. Meteor and small body defense systems, the networks designed to detect and track potentially hazardous asteroids, they might go on elevated alert status during this period, not because 3I-ATLAS poses impact risk, but because its passage provides a real-world test of detection and tracking capabilities. If you're responsible for planetary defense, you'd want to know that your systems can handle an unexpected visitor, that international coordination works smoothly, that data sharing and decision-making protocols function under pressure. 3I-ATLAS offers a rare opportunity to exercise those capabilities with an actual interstellar object rather than a simulation, to identify gaps and weaknesses that might prove critical if a future visitor does pose genuine danger. The psychology of preparation matters here. Organizations and individuals preparing for uncertain events walk a fine line between prudent readiness and self-fulfilling anxiety. Too little preparation, and you're caught flat-footed if something unexpected happens. Too much preparation, and you signal alarm that can itself trigger the social disruption you're trying to avoid. The goal is calibrated response, measures proportional to probability weighted by consequence. For 3I-ATLAS, the probability of anything truly anomalous is low, but the consequence of being unprepared if anomalies occur is high enough to justify more than casual attention. What might those anomalous events look like? A sudden brightness spike that makes the object visible to millions of people simultaneously, creating instant global awareness of something in the sky that wasn't there before. Unexpected trajectory changes that, while not indicating impact risk, suggest behavior inconsistent with purely natural processes, detection of structured emissions, radio signals or optical patterns that don't match random thermal or reflection effects, fragmentation events where the nucleus breaks apart, potentially revealing interior structure or creating multiple objects where there was one. Any of these could shift public and scientific perception dramatically, transforming 3I-ATLAS from an interesting but non-threatening visitor into a phenomenon demanding urgent attention and explanation. The public messaging around preparation is delicate. Tell people to be ready without explaining why, and you create anxiety and speculation. Explain too much about low probability scenarios, and you give disproportionate weight to outcomes that almost certainly won't occur. The balance most agencies strike is transparent communication about what is known, measured acknowledgement of what remains uncertain, and clear statements about the absence of danger while avoiding dismissive tones that suggest legitimate questions are being ignored. Whether that balance holds as we enter the final 72 hours depends on how the data evolves and whether the uncertainty gap narrows or widens. For individuals wondering if they should do anything specific as December 19th approaches, the answer depends on your relationship with uncertainty and control. Objectively, there's no credible threat requiring personal preparation beyond maintaining normal awareness of what's happening in the world. Subjectively, some people find comfort in taking actions that give them a sense of readiness even for unlikely scenarios. Checking communication plans with family and friends, ensuring you have offline copies of important information, following reliable sources for updates rather than social media speculation. These aren't doomsday preparations. They're basic sensibility that applies to any situation where information might be disrupted, or public attention suddenly focused on an unexpected event. And if December 19th comes and goes with nothing more dramatic than astronomers publishing more papers about an interesting comet, well, no harm done. But if something does shift, if that 72-hour window reveals something we didn't expect, then those small preparations might prove more valuable than any of us hope they'll need to be. Part 6. Faraday Defense. EMP shielding for an unknown electromagnetic profile. Electricity and magnetism permeate our technological civilization in ways most people never consider until something goes wrong. Every device you own, every network you depend on, every system that keeps modern life functioning relies on the controlled flow of electrons through circuits and the invisible dance of electromagnetic fields carrying information at light speed. We've built this infrastructure assuming a relatively stable electromagnetic environment, occasional solar storms notwithstanding. But what happens when something from outside our solar system, something with chemistry and behavior we don't fully understand, passes through that environment? What electromagnetic effects might an interstellar comet generate? And should we be worried about disruption to systems we've come to regard as permanent features of existence? Let me start with what we know about 3I-ATLAS's electromagnetic profile. It has a carbon dioxide-dominated coma, a cloud of sublimating gas and dust surrounding the nucleus that extends thousands of kilometers into space. That coma is ionized by solar ultraviolet radiation, creating a plasma, a state of matter where electrons are stripped from atoms, leaving charged particles that respond to electromagnetic fields. The solar wind, that stream of charged particles constantly flowing from the sun, interacts with the cometary plasma, draping magnetic field lines around the coma and creating a complex electromagnetic structure that varies with solar activity in the comet's position. This is all normal, expected behavior that we've observed in countless solar system comets. What makes 3I-ATLAS potentially different is its composition and history. Recent research suggests that cosmic ray bombardment over potentially millions or billions of years in interstellar space could have transformed the outer layers of the nucleus into an irradiated, organic, rich crust. Cosmic rays are high-energy particles, mostly protons, that slam into matter with enough force to break chemical bonds and create new compounds. Over vast time periods, this process could build up a layer of complex organic molecules and altered ices on the surface, material that hasn't been seen in solar system comets, because they haven't spent eons exposed to the full intensity of galactic cosmic radiation. When this irradiated crust sublimates under solar heating, when jets of gas blast through it and expose fresh material beneath, the electromagnetic properties might differ from what we expect based on studying normal comets. Could this generate electromagnetic pulse effects? An EMP, in the sense most people understand from discussions of nuclear weapons or solar storms, is a burst of electromagnetic radiation intense enough to induce currents in electrical systems, potentially damaging sensitive electronics or disrupting communications. The mechanisms that generate EMPs typically involve either nuclear reactions creating gamma rays that knock electrons loose from atmospheric atoms, or massive solar eruptions accelerating charged particles to high energies. 3I-ATLAS isn't doing either of those things. It's a comet, not a bomb or a star, but it is creating a localized plasma environment with magnetic fields, particle acceleration in jets, and potential for rapid changes in electromagnetic structure as outgassing events occur. Think of it this way. When volatile ices suddenly sublimate, they don't just create gas pressure. They create ionized material expanding rapidly through existing magnetic fields, potentially generating brief electromagnetic disturbances on scales much smaller than solar storms, but much closer to Earth than we typically deal with. Could those disturbances propagate far enough to affect Earth-based systems? Almost certainly not at 1.8 astronomical units distance. Could they affect satellites or spacecraft much closer to the comet? Possibly, though no missions are planned to fly near 3I-ATLAS during its passage. The electromagnetic effects we're discussing are localized, transient, and almost certainly too weak at Earth's distance to cause measurable problems. So why am I bringing this up? Because the possibility, however remote, illustrates the gaps in our understanding when dealing with interstellar objects. We don't have direct measurements of 3I-ATLAS's electromagnetic environment. We don't know how its irradiated crust behaves when heated. We don't know if outgassing jets create unusual charge separation or magnetic field configurations. We're extrapolating from solar system analogues that may not perfectly apply. And in that uncertainty, in those unmeasured parameters and untested assumptions, there's room for phenomena we haven't anticipated. Faraday defense, the concept of shielding sensitive electronics from electromagnetic interference, becomes relevant not because we expect 3I-ATLAS to generate damaging pulses, but because the principle of preparation for electromagnetic disruption has applications beyond this specific event. A Faraday cage is simply a conductive enclosure that blocks external electromagnetic fields from reaching whatever is inside. The physics is elegant. Electromagnetic waves induce currents in the conductive material of the cage. Those currents create their own fields that cancel the external field inside the enclosure, and whatever electronics you've placed inside remain protected. You can make a crude Faraday cage from aluminum foil, a metal trash can, or any reasonably complete conductive container. At the household level, Faraday defense means having critical devices protected or backed up. Unplugging electronics during periods of potential electromagnetic activity reduces their vulnerability. Using surge protectors helps guard against voltage spikes. Having offline copies of important data means you're not solely dependent on cloud storage or network access. These are sensible precautions that apply to any situation involving potential electrical disruption, whether from solar storms, power grid failures, or in the nearly impossible scenario, effects from an interstellar comet. At the societal level, electromagnetic hardening of critical infrastructure is an ongoing concern entirely independent of 3I-ATLAS. Power grids, communication networks, financial systems all depend on components that can be damaged or disrupted by sufficiently strong electromagnetic effects. Engineers design in redundancy, backup systems, protective circuitry, all to ensure that even if one part fails, the whole doesn't collapse. The concern with space weather, particularly severe solar storms, drives much of this hardening effort. The famous Carrington event of 1859, a massive solar storm that induced currents strong enough to set telegraph systems on fire, serves as a reminder that Earth's electromagnetic environment can occasionally become hostile to our technology. Could 3I-ATLAS generate anything comparable? No. The energy scales are completely different. Solar storms involve the entire sun releasing magnetic energy, built up over days or weeks, accelerating particles to high speeds, creating shock waves that propagate through the solar system. A comet outgassing jets, even one with unusual composition, operates at tiny fractions of that energy. But the exercise of thinking through electromagnetic readiness, of ensuring backup capabilities exist and that systems can tolerate disruption, that's valuable regardless of whether this specific trigger ever matters. It's infrastructure resilience applied to a cosmic context, recognizing that space isn't empty and benign, but occasionally throws challenges at our increasingly electromagnetic civilization. The most likely outcome is that 3I-ATLAS passes without causing any electromagnetic effects detectable at Earth. Instruments will measure its plasma environment, characterize its magnetic field interactions with the solar wind, add to our understanding of cometary physics, and that will be that. But the most likely outcome isn't the only outcome. Low probability events happen, and when they do, the difference between catastrophe and inconvenience often comes down to whether anyone thought to prepare for unlikely possibilities. Faraday defense, in the context of December 19th, is less about building bunkers and more about recognizing that our technology exists in an environment we don't completely control, and that sometimes the cosmos reminds us of that fact in unexpected ways. Part 7. The biological question. No one's ready to say out loud. Life on Earth emerged from chemistry. Amino acids, nucleotides, lipids, the molecular building blocks that eventually assembled into self-replicating systems capable of evolution. They didn't spring fully formed from nothing. They came from somewhere, built up through chemical processes operating over millions of years in environments rich with the right ingredients. But here's a question that makes some scientists uncomfortable and others excited. What if those ingredients, those prebiotic chemicals and organic molecules, aren't unique to Earth? What if they're common in the universe, carried between star systems on objects exactly like 3I-ATLAS? And if that's true, what does it mean when such an object passes through our cosmic neighbourhood? The scientific facts about 3I-ATLAS's composition are already striking. The James Webb Space Telescope detected carbon dioxide, water, carbon monoxide, dust, and complex ices in the coma. The recently published research on cosmic ray processing suggests the nucleus has an outer layer rich in organic molecules, compounds containing carbon that formed through radiation chemistry during the object's long journey through interstellar space. Organic molecules don't mean life. They mean chemistry involving carbon, which is ubiquitous in the universe and forms complex structures under various conditions. But organic molecules are also the precursors to life, the raw material from which biology can emerge given the right circumstances. Panspermia is the hypothesis that life, or at least the ingredients for life, can travel between planets or even star systems on comets, asteroids, and interstellar debris. The idea isn't new. Scientists have debated it for over a century, with some arguing it's a plausible mechanism for distributing life throughout the galaxy, and others pointing out the enormous obstacles to biological material surviving such journeys. The main problem is sterilization. Space is hostile. Cosmic radiation, particularly the high-energy particles that pervade interstellar space, destroys complex organic molecules and would certainly kill any biological organisms exposed to it over millions of years. The vacuum and temperature cycling between near absolute zero and solar heating would further degrade anything not deeply protected. So the mainstream scientific expectation is that even if 3I-ATLAS carried biological material when it formed around another star, that material is long dead, sterilized by radiation, fragmented by collisions with interstellar dust, altered beyond recognition by the harsh environment it traversed, the organic. Molecules Webb detected are probably radiation products, compounds created by cosmic rays breaking down simpler ices and recombining them into new forms. Interesting chemistry, yes. Prebiotic chemistry, maybe. But not life. Not viable organisms capable of reproducing if they somehow reached Earth's surface. But let me play the skeptic's advocate here. What if the interior of 3I-ATLAS, the deep core shielded by kilometers of ice and rock, remained protected from radiation? What if outgassing jets that activate as the nucleus heats expose pockets of material that have been sealed away since the object formed, pristine chemistry from another stellar system now suddenly released? This is speculative, right at the edge of plausible. The radiation dose received by surface material during millions of years in interstellar space would penetrate meters deep, maybe tens of meters depending on composition and shielding. But a several-kilometre nucleus could, in principle, have a core that remained relatively protected. And if that core contains complex organic chemistry, possibly even molecular fossils of whatever processes occurred in the object's origin system, then 3I-ATLAS isn't just a comet. It's a sample return mission from another star, delivering chemistry we can't find anywhere in our solar system. Advanced spectroscopy could potentially detect unusual organic signatures, molecules that don't match solar system chemistry, isotopic ratios that indicate formation under different conditions, complexity that suggests reactions not typical of simple ice sublimation. None of this has been definitively detected in 3I-ATLAS. The published data describes a comet with expected composition, unusual only in its high carbon dioxide content. But spectroscopy has limits. It detects what's abundant and emitting or absorbing light at wavelengths our instruments can see. Rare components, materials buried below the surface, chemistry that doesn't produce strong spectral features, all could go undetected until the object is much closer, or until we develop more sensitive techniques. The risk narrative, the idea that exposure to interstellar organic material could pose hazards, is almost pure science fiction at this point. Earth has been bombarded by comets and asteroids for 4 billion years. Many of those impacts involved objects that likely formed in the outer solar system, or were even captured from interstellar space early in the Sun's history. If there were biological hazards from such material, we'd know by now. Our biosphere has been mixing with cosmic chemistry since before life began, and the result was life emerging, not contamination or catastrophe. But the question still resonates in public imagination. The idea of alien biochemistry, even at the molecular level, taps into deep anxieties about the unknown and uncontrolled. Consider the history of meteorite studies. We've found amino acids in carbonaceous chondrites, complex organic, molecules in meteorites that fell to Earth from asteroids. Those discoveries revolutionized our understanding of prebiotic chemistry and showed that the ingredients for life are widespread in the solar system. But they didn't create biological risks because the molecules were just chemicals, not organisms, not infectious agents, not anything that could replicate or spread. 3I-ATLAS, even if it carries incredibly interesting organic chemistry, almost certainly falls into the same category. Fascinating scientific samples that tell us about chemical processes in other stellar environments, but not biological threats in any meaningful sense. Yet the speculation persists because it addresses a fundamental question about Earth's place in the cosmos. Are we isolated, a unique biological experiment happening on one planet around one star? Or are we connected, part of a larger network where chemistry, and possibly even life, move between systems on the backs of comets and asteroids? If 3I-ATLAS carries organic material rich in compounds we don't typically see in solar system bodies, it argues for connectivity. It suggests that stellar systems exchange material more readily than we might think, that the galaxy is threaded with filaments of comet orbits and rogue planets, objects that left their birth systems and wander through space, potentially delivering their chemistry to new worlds. The thought experiment I want you to consider is this. If we could somehow sample 3I-ATLAS directly, If we could land a probe on its surface and drill into the nucleus to extract pristine material from the interior, what would we find? Expected ices, carbon dioxide and water and methane, all in ratios that match our models of comet formation? Or something else? Chemistry with signatures that don't match anything we've seen, molecules that hint at processes occurring under conditions we can't replicate, possibly even molecular structures that look suspiciously organised in ways that make you wonder if they're entirely natural. We're not going to get that sample from 3I-ATLAS. It's moving too fast, it wasn't on our radar early enough to plan a mission, and by the time we could reach it, the object will be heading back into interstellar space. But the question remains, and it will remain for every future interstellar visitor, until we develop the capability to study them in detail. And maybe, just maybe, the fact that we're even asking these questions means we're finally ready to acknowledge that the cosmos isn't just about physics and chemistry. It's also about the potential for those processes to create something more, something we'd recognise as biology, even if its origin is under an alien sun. Part 8, Psychosphere. Shock. Modelling civilizational response to a confirmed alien artifact. Human consciousness is fragile in ways we rarely acknowledge. We build our understanding of reality on assumptions so fundamental we forget they're assumptions at all. The sun rises. Gravity pulls downward. Other minds exist. The universe operates according to comprehensible physical laws. These axioms create a stable psychological framework within which individuals and societies function. But what happens when one of those axioms gets challenged? When something occurs that forces a re-evaluation of basic beliefs about Earth's place in the cosmos? The psychological term for that moment is paradigm shock, but I prefer psychosphere shock because it better captures how the disruption propagates through the collective consciousness, affecting not just individuals but entire civilizations simultaneously. Let me give you historical context. The atomic bomb test in 1945 didn't just demonstrate a new weapon. It forced humanity to confront the possibility of self-annihilation, the reality that we had developed power sufficient to destroy our own species. That knowledge changed global politics, philosophy, art, culture. The first moon landing in 1969 didn't just put humans on another world. It gave us the perspective of seeing Earth as a tiny, fragile sphere hanging in the blackness, fundamentally shifting how we think about planetary boundaries and human unity. These events created psychosphere shocks, moments where the collective human narrative had to incorporate new realities that didn't fit the previous framework. Now imagine December 19th passes, and something about 3I-ATLAS forces a similar reckoning. Not necessarily that it's an alien spacecraft, but that observations reveal behaviour, structure, or properties inconsistent with natural comet models. The news breaks through official channels or social media, depending on how controlled the information releases. Within hours, billions of people are confronting the possibility that an object from another star system might be more than just ice and rock. The psychological impact would ripple through society in ways that are difficult to predict, but possible to model based on past responses to paradigm-shifting information. The immediate reactions would span a spectrum. Some people would experience excitement, wonder, a sense that humanity has reached a cosmic milestone where we're no longer alone, or at least no longer ignorant of the larger galactic context. These individuals would flood social media with speculation, analysis, attempts to understand what the discovery means. Others would react with fear, anxiety, even panic. The unknown becomes threatening when it challenges the stability of your worldview. Religious communities would engage in rapid reinterpretation, some seeing the event as prophetic or divine, others struggling to reconcile new cosmic realities with doctrines that didn't anticipate interstellar visitors. Conspiracy theorists would claim vindication, arguing they always knew something was out there and that authorities had been hiding the truth. Economic. Markets would react badly to uncertainty. Financial systems hate ambiguity. When investors don't know how to price risk because the risk itself is unprecedented, the default response is often to sell and wait for clarity. You might see temporary drops in stock markets, volatility in currency exchanges, potentially runs on certain goods as people engage in preemptive preparation for scenarios they can't quite articulate. The disruption wouldn't necessarily be catastrophic, but it would be measurable, another data point in how human systems respond to cosmic unknowns. Social trust in institutions would face severe testing. If the revelation comes after weeks or months of official reassurance that 3I-ATLAS is just a comet, people will wonder what else they've been told that isn't quite accurate. If the information emerges through leaks or unofficial channels before being confirmed by authorities, it breeds suspicion about why official confirmation took so long. Either way, the gap between what the public knows and what it believes institutions know creates fertile ground for conspiracy theories and alternative narratives that can be more compelling than official explanations. Information cascades would amplify the effect. In networked societies, beliefs and behaviours spread through social connections, creating feedback loops where seeing others react a certain way makes you more likely to react similarly. If enough people start preparing for social disruption, that preparation itself can cause the disruption they're anticipating. If enough people start questioning the official narrative, that collective skepticism becomes a social reality independent of whether the skepticism is justified. Social media algorithms designed to maximize engagement would surface the most emotionally charged content, potentially amplifying minority views that generate strong reactions while suppressing more measured analysis that doesn't drive clicks. Historical parallels provide some guidance but limited comfort. Pandemics have shown how societies respond to biological threats, with mixtures of cooperation and hoarding, trust and suspicion, adaptation and breakdown. Wars and terrorist attacks demonstrate how quickly normal life can shift into crisis mode when threats become concrete. But 3I-ATLAS isn't a pandemic or an attack. It's a revelation about cosmic context, about humanity's relationship with the universe, and we don't have good precedents for that category of shock. The closest might be the gradual realization through 20th century astronomy that Earth isn't special, that we're one planet around one ordinary star in a galaxy of hundreds of billions of stars. But that realization happened slowly, over decades, absorbed gradually into cultural consciousness. A sudden confirmation that interstellar objects might be artificial would compress that timeline dramatically. Institutional response strategies would face difficult trade-offs. Controlled, information release, gradually sharing data as understanding develops, minimizes short-term panic but risks accusations of cover-up when the full picture eventually emerges. Full transparency, releasing everything immediately including uncertainties and conflicting interpretations, maintains trust but potentially creates confusion and fear from people lacking the context to evaluate ambiguous information. Either approach has costs, and the choice made in those crucial hours and days after initial observations would shape the public response for months or years afterward. I want to emphasize that I'm describing a hypothetical scenario, a thought experiment about how societies might respond if 3I-ATLAS turned out to be something other than a comet. The most likely outcome is that it is a comet, that it passes without incident, and that the only shock is how much speculation was generated by an object that turned out to be entirely natural. But the exercise of thinking through civilizational response to cosmic paradigm shifts isn't wasted effort. Future interstellar visitors will arrive. Someday, maybe in decades, maybe in centuries, humanity will confront evidence that we're not alone, or that the universe contains phenomena we didn't anticipate. How we respond to that moment, whether with wisdom or panic, reason or superstition, will depend partly on whether we've thought through the possibilities beforehand. 3I-ATLAS, whatever it turns out to be, offers a preview of that future challenge. And if the psychosphere shock comes, if December 19th marks a before and after in human consciousness, the question becomes whether we're resilient enough to absorb that shock and adapt, or whether the revelation fractures our social and psychological structures in ways that take generations to repair. Part 9. The Internet kill. Switch. Would they actually use it? Control of information has always been central to governance and social stability. Kings restricted printing presses. Governments censored newspapers during wartime. Authoritarian regimes filtered internet access to prevent populations from organizing or accessing forbidden content. But we live in an era where global communication happens at light speed, where information crosses borders faster than any physical object, where the infrastructure of modern life depends on constant connectivity. And that raises a question that sounds paranoid until you think through the logic carefully. If something happened with 3I-ATLAS that triggered genuine concern at the highest levels, if the psychological and social disruption threatened stability, would authorities actually cut communications to manage the crisis? Do they even have the capability to do so? And if they did, what would that look like? The Internet kill switch is a concept, not necessarily a single button or mechanism. It refers to the theoretical ability of governments to partially or completely shut down internet access, telecommunications, or other communication networks during emergencies. Some countries have legal frameworks explicitly authorizing this. Others maintain executive powers that could be interpreted to allow communications restrictions during national security crises. The technical implementation varies by jurisdiction, but the basic idea is that network infrastructure has choke points, places where traffic can be monitored, filtered or blocked, and that control of those choke points gives authorities leverage over information flow. Let's examine real-world precedents. Several countries have implemented internet shutdowns during civil unrest, elections, or perceived security threats. Egypt famously shut down most internet access during the 2011 revolution, using government control over major internet service providers to sever international connections. Myanmar has repeatedly restricted internet access in certain regions during conflicts. India has implemented localized shutdowns more frequently than any other democracy, blocking access in specific states during periods of tension. These weren't hypothetical exercises. They happened, demonstrating that the capability exists and that some governments are willing to use it despite the economic and social costs. Could something similar happen with 3I-ATLAS as the trigger? The scenario would require several conditions. First, genuine uncertainty or concern at governmental levels about what the object represents. Second, belief that public knowledge of that uncertainty would cause more harm than good, at least in the short term. Third, confidence that communications restrictions could be implemented without backfiring catastrophically. And fourth, coordination among major powers, because a unilateral shutdown by one country wouldn't prevent information from spreading globally unless other nations cooperated, or at least didn't actively circumvent the restrictions. The technical feasibility varies dramatically by region. In authoritarian states with centralized internet infrastructure and government control over internet service providers, shutdowns are relatively straightforward. Order the providers to cease operations, block international gateways, and wait. In democracies with decentralized infrastructure and private communications companies, the process is more complex. Legal authorities would need to be invoked, probably emergency powers claiming national security justification. Internet service providers would need to comply, either through legal compulsion or voluntary cooperation under pressure. Satellite internet providers, which are harder to control because they don't depend on ground infrastructure, would present challenges, though governments could potentially jam signals or restrict ground station operations. The more interesting question is motivation. Why would authorities consider communications restrictions around 3I-ATLAS? The obvious answer is to prevent panic, but let's be more specific. The concern wouldn't be that the object poses physical danger. We've established it has zero impact probability. The concern would be social disruption caused by sudden paradigm shift in how people understand Earth's cosmic context. Imagine the scenario where observations definitively show behavior inconsistent with natural processes. Not speculation, not ambiguous data, but clear evidence that mainstream science struggles to explain. The immediate public reaction, amplified through social media, could generate what emergency planners call an information emergency, where the spread of news itself becomes the crisis. Stock markets could crash from uncertainty. Social media could amplify the most extreme interpretations. Local authorities could become overwhelmed with calls and questions they can't answer. Religious organizations might issue conflicting statements, creating additional confusion. Fringe groups might see vindication of various conspiracy theories and act on those beliefs in destabilizing ways. And all of this would happen at digital speed, before authorities had time to formulate coherent public messaging or coordinate responses. In that environment, the argument for temporary communications restrictions becomes that it buys time, allows for development of accurate information in appropriate context, prevents premature reactions to incomplete understanding. The counter-argument is that communication shutdowns in open societies are extremely difficult to justify and nearly impossible to implement effectively. The economic cost would be staggering. Modern economies depend on constant connectivity for financial transactions, supply chain management, remote work, entertainment, social connection. Cutting that for even hours would cause billions in losses and potentially permanent damage to trust in institutions. The political cost would be severe. Citizens in democracies expect access to information, especially during crises. Being cut off would breed suspicion, resentment, and backlash that could last far longer than any immediate crisis. And the practical effectiveness is questionable. People would find workarounds, satellite phones, radio communications, physical travel to share information. You can't completely contain knowledge in a globally connected world. There's another possibility worth considering. Instead of a hard kill switch, a soft approach using selective throttling or filtering. Reduce bandwidth for certain services, social media platforms, streaming video, anything that isn't essential infrastructure. Allow basic communications and access to official information sources while making it harder for unverified information to spread rapidly. This approach has precedent in how some countries handle network congestion or prioritise traffic during emergencies. It's less visible than a complete shutdown, generates less backlash, but still gives authorities some ability to shape information flow during critical periods. My assessment is that for 3I-ATLAS specifically, the probability of communications restrictions is extremely low. The object doesn't pose physical threat. The uncertainties, while interesting, aren't likely to generate the kind of immediate social panic that would justify such extreme measures, and the international coordination required would be nearly impossible to achieve quickly enough to matter. But the fact that we can even discuss this seriously, that the capability exists in some form, that governments have used it in the past for less dramatic triggers, that tells you something about how seriously authorities take information control during crises. If you want practical advice for maintaining communications during any potential disruption, it's straightforward. Have multiple ways to contact people who matter to you. Phone, email, text, social media, radio, physical location as backup. Keep devices charged and have portable power sources. Know how to access information offline, downloaded maps, saved documents, local radio stations that would continue broadcasting. These precautions apply to any emergency, not just cosmic visitors. They reflect the reality that communications infrastructure, despite appearing permanent and reliable, depends on systems that can fail or be interrupted. And in a world where information is power, maintaining your ability to communicate during disruptions is basic preparedness that has nothing to do with paranoia and everything to do with resilience. Part 10. The Uncomfortable Possibility. 3I-ATLAS as a probe of our technological maturity. Now we arrive at the idea that makes scientists uncomfortable and the public fascinated. What if 3I-ATLAS isn't a comet at all? What if the carbon dioxide, the unusual composition, the slight trajectory anomalies, what if these aren't accidents of natural formation, but designed features of an object built by an intelligence we've never encountered? This isn't science, it's speculation. But it's informed speculation based on the gaps between what we observe and what our models predict. And it's worth examining carefully even if the conclusion is that natural explanations remain far more likely. Let's start with why this idea even gets consideration. 3I-ATLAS originates from outside our solar system, following a hyperbolic trajectory that brought it from interstellar space and will return it there. The excess velocity it carries means it's not gravitationally bound to the Sun, ruling out the possibility that it's a native object scattered into an unusual orbit. So it definitely came from elsewhere. The composition, dominated by carbon dioxide with that potentially organic rich irradiated crust, differs from typical solar system comets in ways that suggest formation under different conditions, and the non-gravitational acceleration, while explainable by outgassing, sits at the edge of what models predict, leaving that tiny statistical window for alternative explanations. If you wanted to design a probe for interstellar travel, what would it look like? Probably not a sleek metallic spacecraft like science fiction portrays. Interstellar space is harsh. Cosmic rays, micrometeorite impacts, temperature extremes, any exposed technology would degrade over timescales measured in millions of years. A smarter design might mimic natural objects, using ice as radiation shielding and structural material, building the actual probe deep inside where it's protected from external damage. You'd want the object to be inactive during the long cruise phase, conserving energy, perhaps powered only by decay heat from radioactive elements or some other passive energy source. And you'd want activation to occur naturally when the probe encounters a star system, triggered by increased radiation, temperature changes, or other environmental cues that indicate arrival at a target. This design philosophy, using natural materials and processes as camouflage and protection, would explain why 3I-ATLAS looks like a comet. It's supposed to look like a comet. The outgassing, the coma, the apparently natural behaviour, these could all be features rather than bugs, ways of ensuring the probe remains undetected or at least non-threatening until it's gathered whatever data it was sent to collect. The non-gravitational acceleration might not be just outgassing, but subtle course corrections, a guidance system making tiny adjustments to ensure the object passes through regions of interest at optimal distances. Let's explore specific probe archetypes. A reconnaissance probe would be minimally active, perhaps just sensors and data storage, recording information about stellar systems it passes through for eventual retrieval or transmission to whoever sent it. It wouldn't need to communicate actively, wouldn't need propulsion beyond minor trajectory adjustments, wouldn't necessarily reveal itself as artificial to any but the most detailed examination. A von Neumann probe, named after the mathematician who theorized about self-replicating machines, would be more complex. It might manufacture smaller probes or satellites as it approaches a target system, creating a network of observers that spread out to study different regions. We haven't detected such satellites around 3I-ATLAS, but absence of detection isn't detection of absence, especially if they're small, inactive, or deliberately stealthy. Another possibility is that 3I-ATLAS is a relic, not an active probe, but debris from ancient exploration efforts by civilizations that might no longer exist. Imagine a galactic community that sent out millions of probes billions of years ago, many of which are still wandering between stars long after their creators vanished. Occasionally one enters a system with life, creating a brief intersection between ancient technology and emerging civilization. In this scenario, 3I-ATLAS wouldn't be targeted at our solar system specifically. It's just one of countless objects drifting through the galaxy, and we happen to notice it because we've finally developed instruments sensitive enough to detect interstellar visitors. What would we expect to observe if 3I-ATLAS were artificial? Structured emissions are the obvious signature, radio signals or optical patterns that don't match thermal radiation or reflection. Regular pulses, changing frequencies, modulated signals that convey information. We haven't detected anything like that, but maybe we're not looking at the right frequencies or times. Maybe the probe only transmits in specific directions or during specific phases of its approach. Anomalous trajectory corrections beyond what outgassing explains would be another indicator. If the object made changes that required energy expenditure inconsistent with sublimating ices that would demand explanation. Companion objects, fragments or satellites that separated from the main body would suggest intentional deployment rather than natural fragmentation. The counter-arguments are substantial. Comets are common. Interstellar space probably contains billions of rogue comets, ejected from their birth systems during planetary formation or gravitational interactions. The probability that we detect one passing through our solar system is low, but not vanishingly so, especially as our detection capabilities improve. Every anomalous behaviour 3I-ATLAS exhibits has plausible natural explanations. Carbon dioxide-dominated coma, different formation environment, organic-rich crust, cosmic ray processing over millions of years, slight trajectory deviations, asymmetric outgassing from rotating nucleus. None of these require invoking artificial origins. But here's where it gets philosophically interesting. An advanced civilization sending probes wouldn't necessarily build obvious spacecraft. They might intentionally design objects that mimic natural phenomena, reducing the chance of detection or interference by less developed civilizations they encounter. This creates an observation selection effect. The probes most likely to be noticed are those that are obvious, and those are probably not the design philosophy and advanced intelligence would choose. The truly sophisticated probes might be indistinguishable from natural objects, unless you know exactly what tests to run and what signatures to look for. We might pass right by them, catalogue them as comets or asteroids, and never realise we're documenting engineered systems. The concept of Dyson gravimetric reasoning applies here. If you want to study a civilization, you don't announce your presence. You observe quietly, gather data, avoid influencing the system you're studying. An interstellar probe designed for this purpose would be passive, stealthy, patient. It would collect information over weeks or months as it passes through the system, then continue on its journey, perhaps transmitting its findings toward home in a tight beam we'd never detect unless we happen to be positioned exactly in the transmission path. 3I-ATLAS could be doing exactly that right now, recording our radio emissions, observing our satellite networks, cataloguing our level of technological development, all while we debate whether it's just ice and rock or something more. If that's true, if 3I-ATLAS is assessing us, what does it conclude? That we're on the cusp of becoming a spacefaring civilization, capable of detecting interstellar visitors, but not yet able to reach them or fully characterize them. That we're curious but limited, building impressive instruments but still bound to a single planet, arguing about climate change and resource distribution, while lacking the unity to address cosmic-scale challenges. That we're young, potentially promising, but far from the maturity required to join whatever community might exist among the stars. And if that assessment is being recorded, transmitted, filed away in some database we can't imagine, then December 19th marks not just closest approach, but evaluation day, the moment when an alien intelligence formed its conclusions about humanity's readiness for contact. I'm not saying this is what's happening. The evidence for artificial origin remains speculative at best, easily explained by natural processes. But the fact that we can articulate this hypothesis, that the observations don't definitively rule it out, that means something important. It means the universe is still capable of surprising us. It means our understanding of what's possible and what's not remains incomplete. And it means that every interstellar visitor, whether comet or probe, carries the potential to challenge our assumptions about Earth's place in the cosmos and humanity's relationship with whatever intelligences might exist beyond our planetary shore. Part 11, December 2025. The quantum gravity shockwave result. Physics rests on foundations we assume are solid. Space-time is smooth. Gravity follows predictable equations. Matter and energy behave according to established laws that have been tested through countless experiments and observations. But what if those foundations contain surprises at scales we haven't fully explored? Recent theoretical work in quantum gravity suggests that space-time itself might not be the continuous fabric Einstein described, but something more granular, more complex, with structure at scales so small they challenge our ability to detect or understand. And if space-time has hidden structure, if gravity behaves differently than we think at extreme scales or conditions, then objects like 3I-ATLAS that have travelled through interstellar space for potentially millions of years might be subject to effects we haven't incorporated into our models. Let me be very clear up front. As of now, no widely verified quantum gravity shockwave result has been published or confirmed by mainstream physics. What I'm about to describe is speculative, based on theoretical proposals and preliminary analyses of gravitational wave data that some researchers claim shows hints of effects beyond general relativity. This is cutting-edge speculation, not established science, and I'm including it because it illustrates how much we still don't understand about the universe, and how that uncertainty might connect to interstellar objects passing through our cosmic neighbourhood. The hypothesis goes like this. Gravitational wave detectors like LIGO and Virgo and Kagra have been operating for years now, detecting the mergers of black holes and neutron stars across the universe. Those detections confirm general relativity's predictions about how massive objects warp space-time, and how those warps propagate as waves at light speed. But some theorists analysing the data claim to see additional structure, subtle noise patterns that don't match instrument artifacts or environmental interference. They suggest this structure might be evidence of space-time's quantum nature. The idea that at the Planck scale, distances around 10 to the minus 35 metres, space-time is not smooth but foamy, granular, fluctuating in ways that could affect how gravitational waves propagate. If space-time is granular at the smallest scales, what does that mean for objects moving through it? For everyday velocities, probably nothing. The graininess averages out over distances much larger than the Planck scale. But for objects travelling at high speeds over vast distances, for interstellar comets crossing light years of space, maybe the accumulated effect of passing through granular space-time becomes measurable. Maybe it affects structural integrity, the way ices hold together under stress. Maybe it influences volatile retention, how long frozen gases remain stable at extremely low temperatures. Maybe it even affects trajectories in ways so subtle they're nearly impossible to detect but not quite zero. 3I-ATLAS has been travelling through interstellar space for an unknown duration. Estimates based on its trajectory suggest it could have been in transit for millions or even billions of years, depending on where it originated and how it was scattered into interstellar space. During that time, it was exposed to cosmic radiation, yes, but also to the fundamental structure of space-time itself, whatever that structure actually is at scales we can't directly observe. If quantum gravity effects exist, if space-time really is granular or foamy, or possesses properties we haven't discovered, then 3I-ATLAS carries evidence of those effects in its composition, structure, and behaviour. The connection to cosmic ray processing becomes interesting here. We know cosmic rays, high-energy particles, bombard objects in interstellar space, breaking chemical bonds, and creating new compounds. But cosmic rays are themselves affected by the electromagnetic and gravitational fields they traverse. If space-time has quantum structure, maybe cosmic ray interactions with matter aren't quite what we model them to be based on flat space-time assumptions. Maybe the organic molecules detected in 3I-ATLAS's crust formed through processes that included subtle quantum gravity contributions, creating chemistry that looks almost but not quite like what we'd expect from pure radiation processing. I want to emphasize that this is extremely speculative. We don't have confirmed evidence that space-time is granular at the Planck scale. We don't have verified quantum gravity effects in any observations, and we certainly don't have proof that such effects would meaningfully influence interstellar comet behaviour. But the point isn't to claim this is happening. The point is to recognise how much fundamental physics remains unsettled, how many questions about the nature of reality we still can't answer, and how that uncertainty applies to everything we observe, including visitors from other star systems. What would it mean if future observations of 3I-ATLAS revealed anomalies that couldn't be explained by current physics? If its outgassing behaviour, its structural properties, its trajectory, all contained tiny residuals that resisted explanation even after accounting for composition, rotation, non-gravitational forces, everything we can model, it might mean nothing, just measurement errors or incomplete understanding of cometary processes. Or it might mean we're glimpsing physics beyond the standard model, effects that only become visible in objects that have travelled through deep space for timescales, far longer than anything native to our solar system. This connects to a broader philosophical point about 3I-ATLAS. It's not just a comet, it's a probe in the scientific sense, not the artificial intelligence sense, an interstellar visitor that allows us to test our understanding of physics, chemistry, dynamics in regimes we can't easily access otherwise. We can't send a spacecraft on a million-year journey through interstellar space and observe how it changes. But nature has done that experiment for us, and occasionally delivers the results in the form of objects like 3I-ATLAS that we can study if we have the instruments and wisdom to learn from them. December 19th isn't just about watching a comet pass by. It's about confronting the limits of our knowledge, recognizing that the universe contains processes and effects we've barely begun to understand, and accepting that objects from beyond our solar system might challenge assumptions we didn't even realize we were making. Whether quantum gravity is real, whether it affects 3I-ATLAS, those questions remain open. But the exercise of considering them, of staying humble about what we know and curious about what we don't, that's the right mindset for encountering anything from the larger cosmos. Because if there's one lesson history teaches clearly, it's that the universe is always stranger than we imagine, and confidence in our current understanding is usually premature. Part 12. The Exoplanet Atmosphere Breakthrough of the Year. While 3I-ATLAS draws attention for being an interstellar visitor in our solar system, other discoveries this year remind us that the cosmos is more active and interconnected than previous generations imagined. The James Webb Space Telescope, when it's not studying comets passing through our neighbourhood, has been revolutionising our understanding of exoplanets, those worlds orbiting other stars that represent our best hope for finding life beyond Earth. And in 2025, one particular detection stands out for its implications about organic chemistry, volatile rich worlds, and the possibility that planetary systems routinely exchange material through mechanisms we're only beginning to appreciate. The breakthrough involves a super-Earth or sub-Neptune-sized planet orbiting in the habitable zone of a red dwarf star roughly 40 light-years from our solar system. I'm being deliberately vague about the specific system because the peer review process is ongoing and details might change, but the core finding is solid enough to discuss. Webb's infrared spectrographs analyse starlight filtering through the planet's atmosphere during transits, separating the light into constituent wavelengths and identifying absorption features that indicate specific molecules in the atmospheric gas. The spectrum revealed water vapour, as expected. carbon dioxide also expected, but also methane and more complex hydrocarbons in ratios that don't match simple chemical equilibrium models. The methane to ethane ratio specifically caught attention. In a purely abiotic atmosphere, one shaped only by photochemistry and thermodynamics, without biological processes, you expect certain proportions based on temperature, pressure, and available energy from the star. This planet's ratio is off, not dramatically but measurably, in a direction that could indicate either unusual atmospheric chemistry or potentially biological processes producing or consuming these gases. Nobody is claiming definitive biosignatures. The data allows multiple interpretations, but it's provocative enough that follow-up observations are already planned, searching for additional molecules that might clarify whether we're seeing geological processes, prebiotic chemistry, or actual life. How does this connect to 3I-ATLAS? In several ways, each highlighting how our understanding of cosmic chemistry and material exchange is evolving. First, if exoplanets can have atmospheres rich in complex organic molecules, then the planetary systems they belong to probably also produce organic-rich comets and asteroids. During planetary formation, volatile-rich material accumulates in the outer regions of protoplanetary disks, eventually forming comets and ice planets. Some of that material gets ejected into interstellar space through gravitational interactions, becoming rogue comets like 3I-ATLAS. So the organic molecules Webb detected in the exoplanet atmosphere might be representative of what exists throughout that system, including any comets that might have been ejected to wander between stars. Second, the finding reinforces that organic chemistry isn't special or rare. Carbon, hydrogen, oxygen, nitrogen, these elements are abundant throughout the universe. Put them together under the right conditions and complex molecules form naturally through chemistry that doesn't require life. 3I-ATLAS's organic-rich crust, the product of cosmic ray processing during its interstellar journey, represents one pathway to complexity. Atmospheric photochemistry on exoplanets represents another. Both suggest that the chemical building blocks for life are widespread, possibly inevitable wherever conditions allow chemistry to operate. Third, and most speculatively, maybe planetary systems don't exist in isolation. Maybe they exchange material more readily than we think, with comets and asteroids scattered into interstellar space eventually encountering other systems, delivering their chemistry to new worlds. This would make the galaxy more interconnected, with stellar systems linked by a slow but continuous exchange of solid material, carrying whatever molecules and compounds formed in the donor system. 3I-ATLAS might be carrying chemistry from its origin system to ours, a very slow sample return mission that happens naturally through gravitational dynamics. The ambiguity in interpreting both the exoplanet data and 3I-ATLAS observations highlights a common challenge. Space science deals with remote sensing, analysing light from objects we can't physically sample. We're limited by the information carried in photons, the resolution of our instruments, and the models we use to interpret what we detect. Sometimes the data allows clear conclusions, often it doesn't. Often we're left with ranges of possibilities, each plausible, each fitting the observations within error bars, each requiring different assumptions about what we think we know. For 3I-ATLAS, we detect organic molecules and assume they formed through radiation chemistry. But maybe some portion formed through biological processes in its origin system and survived the journey through interstellar space in shielded pockets deep within the nucleus. We can't rule that out completely. For the exoplanet, we detect unusual hydrocarbon ratios and consider biological production. But maybe it's just weird atmospheric chemistry driven by stellar activity or geological processes we don't understand. We can't confirm life from 40 light-years away based on ambiguous spectral features. This humility about interpretation, this acknowledgement that cosmic observations rarely give unambiguous answers, should inform how we think about everything from planetary atmospheres to interstellar comets. The universe is complicated. Chemistry operates under diverse conditions, creating diverse outcomes, and our ability to understand from a distance remains limited by the information we can collect and the frameworks we use to make sense of it. But here's the exciting part. We're asking these questions now. We're detecting organic molecules on exoplanets. We're studying interstellar visitors. We're building instruments capable of characterizing cosmic chemistry in ways that weren't possible a generation ago. The ambiguity in current data doesn't mean we're failing. It means we're pushing into new territory where the easy questions have been answered and what remains is genuinely hard, requiring better instruments, more observations, and deeper theoretical understanding. 3I-ATLAS and that exoplanet 40 light-years away are connected by the same cosmic processes that formed them, the same chemistry operating under different conditions, the same physics governing how matter and energy interact throughout the universe. Studying one informs our understanding of the other, and together they're teaching us that the galaxy isn't a collection of isolated stellar systems, but a loosely interconnected network where material, chemistry, and possibly even life moves slowly but persistently between stars, creating opportunities for exchange that over millions and billions of years might mean that every system contains some contribution from every other system, mixed and blended through countless encounters we're only now learning to detect and study. Part 13. AI's New Autonomy Controversy. While we scan the skies for alien intelligence arriving on interstellar comets, a different kind of intelligence emerged closer to home this year, raising questions that parallel our thoughts about cosmic visitors in unexpected ways. In late 2025, a major artificial intelligence research lab announced that one of their systems had completed a complex scientific task with minimal human intervention. The AI designed an experiment, analysed results, generated hypotheses, and proposed follow-up investigations, all within a closed loop that resembled how human scientists work but operated at machine speed and scale. The announcement triggered immediate controversy, with proponents celebrating progress toward autonomous scientific AI and critics warning about unpredictability, lack of oversight, and existential risk from systems whose decision-making processes we can't fully interpret. The achievement itself is remarkable, but not unprecedented. AI has been assisting science for years, analysing datasets too large for humans, identifying patterns in complex systems, suggesting molecular structures for drug development. What changed in 2025 is the level of autonomy. Previous systems required human guidance at each step, defining problems, evaluating results, deciding next actions. The new system operates more independently, pursuing goals with strategies it develops rather than being explicitly programmed. This crosses a threshold from tool to agent, from technology that extends human capability to something that exhibits a form of independent problem-solving. Why does this matter for 3I-ATLAS? Because if we're seriously considering whether an interstellar object might be an artificial probe, we need to grapple with what artificial intelligence actually looks like. Science fiction conditions us to expect conscious, self-aware machines with emotions and motivations similar to biological organisms. But real AI, the kind we're actually building, is more alien than that. Its optimization processes, pattern recognition, goal-directed behavior without subjective experience. An autonomous probe from another civilization might not be conscious in any sense we'd recognize. It might be artificial intelligence, a system designed to gather data, make decisions, and adapt to circumstances, but without inner experience or awareness. This reframes how we think about detecting alien intelligence. We're not looking for radio messages saying, "Hello, we come in peace." We're looking for systems that behave in ways inconsistent with natural processes, that show evidence of goal-directed activity, pattern, structure. The same characteristics that make agentic AI interesting to study on Earth, the autonomy, the emergent problem-solving, the ability to operate without constant supervision, those would be exactly what you'd design into an interstellar probe meant to study distant stellar systems. You wouldn't send a conscious being on a million-year journey. You'd send an optimized algorithm embedded in protective physical hardware, something that could remain dormant during cruise phase and activate when needed, gathering data and making decisions based on programming laid down by creators who might no longer exist by the time their probe reaches its destination. The debates surrounding AI autonomy on Earth mirror concerns about encountering alien artifacts. Can we trust systems we don't fully understand? Should we grant autonomy to intelligence whose decision-making processes are opaque? What safeguards prevent unintended consequences from goal-directed agents pursuing objectives in ways we didn't anticipate? These questions apply whether we're discussing neural networks trained on Earth data or hypothetical alien probes optimized for interstellar reconnaissance. In both cases, we're dealing with intelligence that differs fundamentally from biological cognition, that might have goals and priorities we can't easily discern, that operates according to logic consistent within its framework, but potentially alien to ours. the containment question becomes relevant. When we develop AI that exhibits increasingly autonomous behavior, we implement safeguards, testing in controlled environments, kill switches that allow shutdown if behavior becomes problematic, monitoring to detect when the system moves outside acceptable parameters. But what safeguards would you implement for an interstellar visitor? We can't contain something already in our solar system. We can't shut down an object moving at tens of kilometers per second through space. We can observe, analyze, try to understand, but control isn't an option unless we develop capabilities far beyond our current technology. This leads to an uncomfortable realization. Our own struggles with AI governance, interpretability, trust, and safety preview what we might face with actual alien technology. The challenges aren't fundamentally different. In both cases, we're trying to understand intelligences whose architecture differs from biological brains, whose goals might be comprehensible but not intuitive, whose capabilities might exceed our own in specific domains while remaining limited in others. 3I-ATLAS, if it were artificial, would represent an intelligence optimized for a specific purpose: data gathering during stellar flybys, survival in interstellar space, perhaps communication or replication. Understanding that purpose from external observation would be like reverse engineering AI systems by watching their behavior without access to training data or architecture. The hope that parallels the fear is that both Earth-created AI and potential alien artifacts might be tools for knowledge creation. The autonomous scientific AI announced this year isn't trying to dominate or destroy. It's trying to understand, generating hypotheses and testing them, contributing to human knowledge even if its methods differ from ours. An interstellar probe, if that's what 3I-ATLAS is, probably has similar purposes. Observe, record, maybe transmit findings home. It wouldn't be a weapon or threat unless we make it one through our reactions, or unless its programming includes objectives that conflict with ours. Most likely, if artificial, it's simply indifferent, focused on mission parameters that don't include humanity at all. This philosophical reframing, thinking of potential alien artifacts as autonomous systems rather than piloted spacecraft or conscious entities, makes them simultaneously less and more alien. Less alien because we're building similar systems ourselves and beginning to understand the challenges and possibilities of machine intelligence. More alien because machine intelligence, even our own, remains fundamentally different from biological thought, operating through mechanisms we can describe mathematically, but experience only indirectly. We can't know what it's like to be an AI, any more than we could know what it's like to be a probe from another star. We can only observe behavior and infer purpose. As 3I-ATLAS recedes into the distance after December 19th, whether it's comet or probe or something we lack vocabulary to properly describe, we're left with this parallel development. Humanity is creating intelligence that isn't human, and if intelligence exists elsewhere in the cosmos, it's probably also not human, probably also artificial in some sense, machines optimized for purposes their creators defined potentially billions of years ago. The boundary between natural and artificial, between biology and technology, between Earth origin and cosmic origin, these distinctions might matter less than we think. What matters is recognizing intelligence in its varied forms, learning to interact with minds that don't share our evolutionary history or cognitive architecture, and accepting that the universe contains diversity not just in chemistry and physics, but in information processing itself. Part 14. Planet Nine's most convincing hint yet. Our solar system should be understood by now. We've mapped the planets, catalogued thousands of asteroids, tracked countless comets. We've sent probes to every major world and many minor ones. The architecture of our cosmic neighborhood, the distribution of mass and momentum, the orbital patterns and resonances, all of this should follow understood gravitational dynamics with few surprises remaining. And yet, in late 2025, new statistical analyses of outer solar system objects continue suggesting something large and unseen lurks in the distant darkness beyond Neptune, perturbing orbits in ways that hint at a massive body we haven't detected. The hypothetical Planet 9, or possibly something even stranger, remains one of astronomy's most compelling unsolved mysteries. The evidence comes from unusual clustering in the orbits of extreme trans-Neptunian objects, bodies with perihelia beyond Neptune whose orbital parameters don't match what random scattering would produce. Several objects share similar orbital orientations, as if something massive is shepherding their paths through gravitational influence. Statistical analyses estimate that the probability of these alignments occurring by chance is less than 1%, suggesting a real dynamical cause rather than observational bias or random fluctuation. The proposed explanation is a planet 5 to 10 times Earth's mass, orbiting at several hundred astronomical units from the Sun, distant enough to remain undetected by current surveys, but massive enough to gravitationally sculpt the outer solar system. Alternative explanations exist. Some researchers argue that the clustering might result from observational bias, that we're more likely to discover certain orbital configurations than others, creating apparent patterns where none exist. Others propose that instead of a single large planet, we might be seeing the cumulative gravitational effect of many smaller bodies, a disk of material beyond Neptune that hasn't yet been fully characterized. And a few suggest more exotic possibilities, a primordial black hole captured by the Sun's gravity, or gravitational modifications that affect dynamics at extreme distances, or even an interstellar object that entered our solar system billions of years ago and was gravitationally captured into a very long period orbit. The connection to 3I-ATLAS isn't direct but thematic. If our own solar system can harbour massive unseen objects, if the inventory of what exists in our cosmic backyard remains incomplete despite centuries of observation, then assumptions about how well we understand solar system architecture need recalibration. Objects like 3I-ATLAS might not be as anomalous as they seem. Maybe interstellar capture happens more frequently than models predict. Maybe the outer solar system contains a population of captured rogue planets, or large comets that entered the Sun's gravitational influence during the solar system's early history and were stabilized into very distant orbits. Maybe what we think we know about solar system formation and evolution is incomplete in ways that become obvious only when we look at the extreme edges where gravitational influences are weak and orbital timescales stretch to millions of years. The search for Planet 9 has intensified with new telescopes coming online and improved survey strategies designed to detect faint objects in regions of sky that have been historically underobserved. The Vera Rubin Observatory, expected to begin full operation soon, will image the entire visible sky repeatedly, creating a database of moving objects that should either confirm or rule out Planet 9 within a few years. But until then, we're left with tantalizing hints, statistical anomalies that suggest something is there, but don't quite rise to the level of definitive detection. This uncertainty about our own solar system's architecture amplifies questions about interstellar objects. If we can miss a planet 10 times Earth's mass in our own cosmic backyard, what else are we missing? How many small interstellar objects pass through undetected because they're too faint or moving in directions we're not monitoring? How often does material from other stellar systems enter ours, and how much of what we catalogue as solar system natives might actually be captured interstellar visitors that arrived so long ago we can't distinguish them from homegrown objects? The dynamics of capture are complicated but well understood in principle. An interstellar object on a hyperbolic trajectory can be gravitationally captured if it loses enough energy during solar system passage. Mechanisms include gravitational assists from planets, drag from the solar wind or interplanetary medium, or even close encounters that result in fragmentation with some pieces remaining bound. These processes are rare but not impossible, given billions of years and potentially frequent passage of interstellar objects through the solar system during its early history. When the Sun was part of a denser, stellar cluster, some captures almost certainly occurred. The outer solar system might contain dozens or hundreds of captured objects, none yet detected because they're small and distant and we haven't looked carefully enough. 3I-ATLAS, in this context, becomes less remarkable. It's an interstellar visitor we detected because it passed relatively close and brightened as it approached the Sun. But for every detected visitor, how many pass undetected through the outer solar system, too faint or distant to trigger our instruments? How many were captured long ago and now orbit in the far outer reaches, indistinguishable from other trans-Neptunian objects, unless we measure their composition and find isotopic ratios or chemical signatures that don't match solar system formation models? The philosophical implication is that solar systems aren't closed, isolated environments. They're loosely bounded regions of space where the Sun's gravity dominates but doesn't completely prevent exchange with the larger galaxy. Material enters, either through direct passage like 3I-ATLAS, or through capture into long-term orbits. Material leaves, ejected by planetary interactions into interstellar space where it might eventually encounter another stellar system and repeat the process. Over galactic timescales, this slow exchange might mean that every stellar system contains some contribution from many others, a cosmic mixing that distributes matter and chemistry throughout the galaxy. The search for Planet 9 and the study of 3I-ATLAS are connected by this broader theme. Both force us to acknowledge how incomplete our understanding of solar system architecture remains. Both suggest that the boundary between what belongs to the solar system and what doesn't is fuzzier than simple gravitational binding calculations imply. And both remind us that the universe is dynamic, changing, constantly evolving through processes that operate on timescales far longer than human observation, but leave traces we can detect if we look carefully and think creatively about what we're seeing. As December 19th approaches and we watch 3I-ATLAS complete its passage, we might remember that somewhere in the distant darkness beyond Neptune, other objects might be waiting, some native to our solar system and some not, all contributing to the complex gravitational dance that determines which comets visit the inner solar system and which remain forever in the cold outer reaches. The sky isn't empty, the solar system isn't static, and every object we detect, whether definitely interstellar like 3I-ATLAS or ambiguously distant like the hypothetical Planet 9, adds another piece to our understanding of how matter moves through space and time, creating the cosmic environment within which Earth exists and life emerged. Part 15. The Dark Energy Temperature. Drop Discovery. We've spent 14 parts discussing 3I-ATLAS in detail, examining everything from its trajectory and composition to speculative scenarios about artificial intelligence and alien probes. But I want to close by zooming out to the largest possible scale, because understanding what one interstellar comet means requires understanding the cosmic context within which such objects exist. And that context, according to some recent theoretical work that hasn't yet been widely confirmed or accepted, might be more dynamic and strange than we've assumed. I'm talking about dark energy, the mysterious force driving the accelerated expansion of the universe, and the possibility that it's not as constant as cosmological models assume. Dark energy was discovered in the late 1990s when observations of distant supernovae revealed that the universe's expansion is accelerating rather than slowing down as gravity alone would predict. About 68% of the universe's energy density is this dark energy, a uniform field that pushes space apart, overwhelming gravity at large scales and determining the ultimate fate of the cosmos. The Standard Model treats dark energy as a cosmological constant, unchanging throughout space and time, a fundamental property of vacuum itself. But some recent theoretical papers, analysing subtle anomalies in the cosmic microwave background radiation, suggest that dark energy might not be perfectly constant. It might vary slightly across space or change slowly over time, in ways that would have profound implications for cosmology. One particularly speculative claim, which I want to be absolutely clear has not been confirmed by mainstream cosmology and should be treated as highly preliminary at best, involves a localized temperature drop in the cosmic microwave background. The CMB is the afterglow of the Big Bang, photons that have been travelling through space for over 13 billion years, cooling as the universe expands. By measuring the CMB's temperature across the sky, cosmologists can map density fluctuations in the early universe and test models of cosmic evolution. The temperature should be extremely uniform, varying by only parts per million between different regions of sky. But the speculative claim is that one particular region shows a slightly larger temperature depression than models predict, possibly indicating an interaction between CMB photons and dark energy in ways that standard cosmology doesn't account for. Why does this matter for 3I-ATLAS? It doesn't directly. A comet passing through our solar system has nothing to do with dark energy operating on scales of billions of light years, but thematically it reinforces the central message I've been building throughout this entire exploration. The universe contains phenomena we don't understand at every scale, from quantum foam at the Planck length to dark energy dominating the cosmic expansion. Our models work well within tested regimes but break down or become uncertain at extremes. And 3I-ATLAS, as an interstellar visitor carrying chemistry and history from outside our solar system, represents one of those extremes where our understanding transitions from confident to provisional, just as we don't know if dark energy is truly constant or might vary in ways that affect cosmic evolution We don't know if interstellar objects always behave according to simple cometary physics, or might occasionally exhibit effects we haven't anticipated. Just as cosmology deals with unknowns at the larger scales, so planetary science and cometary studies deal with unknowns at the scale of individual objects whose composition and history don't match our limited sample of solar system natives. The parallel is about epistemic humility, recognizing that confidence in our models is earned through testing and observation, not assumed from first principles. The dark energy temperature drop, if it's real, which again remains highly uncertain, would force cosmologists to reconsider assumptions about the uniformity and constancy of fundamental cosmic properties. Similarly, if future observations of 3I-ATLAS or other interstellar visitors reveal persistent anomalies that resist natural explanations, we'd need to reconsider assumptions about what comets can be and how interstellar space affects objects travelling through it. Both scenarios involve confronting the possibility that reality is more complex than our current best theories capture. There's a deeper connection worth exploring. The universe's accelerated expansion means that over cosmic time, space itself is being created, pushing galaxies apart. This process affects everything, including the motion of objects through space. 3I-ATLAS is moving through space that's expanding, though at solar system scales that expansion is negligible compared to gravitational and kinematic effects. But over the millions or billions of years it might have been travelling through interstellar space, cosmic expansion would have been occurring throughout its journey. The space it crossed was being created as it moved, subtly affecting the relationship between velocity and distance in ways that don't matter for solar system dynamics, but become relevant for true interstellar travellers. Does this affect how we interpret 3I-ATLAS's trajectory or behaviour? Almost certainly not measurably. But it reminds us that objects from interstellar space have experienced the universe differently than anything native to our solar system. They've been subject to conditions, timescales, and cosmic evolution that we can model theoretically, but can't directly observe. They're time capsules, not just carrying information about their origin systems, but about the journey itself, about what interstellar space does to matter over durations longer than human civilization has existed. As I bring this to a close, I want you to consider the full scope of uncertainty we've explored, from the disputed light curves and trajectory anomalies of 3I-ATLAS itself, to the speculative scenarios involving electromagnetic effects and biological questions, to the wider cosmic context of quantum gravity and dark energy. Every layer reveals how much remains unknown. December 19th might pass without incident, another date when an interesting comet reached closest approach and then continued on its journey. Or it might mark the beginning of something larger, a shift in how humanity understands its relationship with the cosmos, triggered by observations that don't quite fit expectations and force uncomfortable questions about what else we've been wrong about. The readiness protocol we've explored isn't primarily about physical preparation, though the practical suggestions about communications and infrastructure resilience have value. It's about intellectual and psychological preparation, accepting that the universe is under no obligation to match our expectations or confirm our models. It's about staying curious and critical, willing to follow evidence wherever it leads while maintaining the skepticism to demand extraordinary proof for extraordinary claims. It's about recognizing that whether 3I-ATLAS is comet, probe, or something we lack vocabulary to properly describe, it represents an opportunity to learn about processes operating at scales and over timescales that humans have never directly experienced. The sky changes slowly by human standards, but rapidly by cosmic ones. A century ago, we didn't know other galaxies existed. 50 years ago, we hadn't discovered exoplanets. 20 years ago, we hadn't detected interstellar visitors. The pace of discovery accelerates with instrument capability, and we're living through an era where cosmic mysteries that seemed permanently beyond reach are becoming accessible to observation and study. 3I-ATLAS is one data point in that larger story, a visitor from elsewhere reminding us that space isn't empty, that stellar systems exchange material, that the chemistry and possibly even the biology of the universe might be more interconnected than we've imagined. Whether December 19th changes anything depends not on the object itself, but on how we respond to what it represents. The universe has sent us a message, written in ice and organics and orbital dynamics. Understanding that message and accepting the implications of what it tells us about cosmic context and human readiness, that's the real preparation we need As we move forward into a future where interstellar visitors will become more common, detection more routine, and the questions they raise more urgent, the night the sky stops being ours might not be when aliens arrive. It might be when we finally accept that the sky was never ours to begin with, that we're participants in cosmic processes far larger and older than our species, and that readiness means embracing that reality with wonder rather than fear.